All right, I'm back. We're on page 294, I think. And we're just going to keep talking about finding derivatives, what it means to be a derivative. Remember, slope of the curve, slope of the tangent line at the exact same point of tangency. A lot going on. We also found in the last video that if we want to find the derivative with respect to x of the natural log of x, that's going to be 1 over x, but we have that additional restriction that x has to be greater than 0. Why does that have to be the case? Because the domain of natural log of x is x greater than 0. So the derivative can't exist where the function doesn't exist, because that doesn't make any sense. Like, how could you have a tangent line at a point where the function doesn't exist? How could the function have a slope at a point where the function doesn't exist? So we need that domain restriction. You're probably going to forget that. You're probably going to lose a point at some point in your life because you forgot that. But like, don't do it. Don't be that person. Be different. We also saw in the last problem that the derivative with respect to x of cosine of x is the negative of the sine of x. And that's another thing you want to memorize, right? And so you should probably think, like, what's the derivative of sine? Well, bust out your calculator and find it, right? Now you know a way to find basically the derivative of almost everything. So you got to, like, take matters into your own hands, find some derivatives, see if you can figure them out. I think you can. If you can't, go back to the video, watch how we did the last one. I think you'll be okay. So let's see what these have to say. So f of x is differentiable at x equals a if f prime of a exists. All right, so you're going to hear that a lot. Function is differentiable at a point. As soon as you know that, you know it means the derivative exists at that point, which means there's a slope, there's a tangent line, a lot of stuff going on. We say that f of x is differentiable on the interval. So this is an interval right here. That's the interval from a to b. If f prime exists for all x in the interval. So this is like a more general statement because you don't want to have to say that a function is differentiable at 1 and 2 and 3 and every number in between. Just say that it's differentiable on the interval from 1 to 3. Differentiable on the interval from 1 to 3 means every point between 1 and 3, I could find the derivative. So there's a slope, there's a tangent line, a lot of stuff going on. If f prime of x exists everywhere that f of x exists, right? So everywhere f of x exists is the domain of f of x. So if on the domain of f of x, f prime exists at every single point, then we're going to say the function is differentiable overall, right? So that's a very strong statement to make. Like cosine of x, for example, is a differentiable function. Natural log of x is also a differentiable function because on their domains, the derivative exists at every single point. We actually haven't really seen examples yet where the derivative fails to exist. We're going to get to that soon. But just know, if I tell you, or anyone tells you, that a function is differentiable, that means that everywhere on the domain of the function, f prime of x exists. Okay, so let's see. If f prime exists for all x in some interval, it's often easier to find a function, blah, 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 right? So this is just saying, instead of calculating the derivative at 1, at 2, at 3, at 4, at 5, let's find a function that just does it, right? So here are the two ways that you can go about doing it. Well, actually, it's not really two ways. Also, I've become disconnected from projecting this. Let's see. All right, I'm back. Okay, so there's two ways that you can go about doing this. There's actually a third way, but like, let's not worry about that right now. So the limit definition using h is the most common one. I don't know why that won out, probably for typographical reasons, because it's easier to type an h than it is to type a delta x. But f prime of x is, so this is, you got two different definitions. You want to be familiar with both of them. I mean, they're basically the same, right? So we get this. So the limit as h approaches 0, f of x plus h minus f of x over h. That's how you find f prime of x. That, in my mind, that's what I think every time someone says find the derivative using the limit definition. If it doesn't say using the limit definition, I would try to find another way. But you can also sometimes, it's not uncommon now that you'll see f prime of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So you could actually change that to pretty much anything. It could be the limit as k approaches 0 of f of x plus k minus f of x over k. Provided everything is in like the correct place, it'll always work out. So you should memorize that. you should have started memorizing it a long time ago because we were calculating limits at specific points and we used basically this definition to do it. So let's see if we can do this problem. Given that f of x equals x cubed plus 5x, compute f prime. Show that f of x is differentiable, and then find the equation of the tangent line at x equals -1. Good. So there's like a lot of things to do here. First, we're going to compute f prime. So f prime of x is the limit as, nope, not x, as h approaches 0 of f of x plus h. So I'm just going to kind of write these down. So x plus h, so it'll be x plus h cubed plus 5x plus h, right? So that's f of x plus h minus f of x. So always you want to put this in parentheses to avoid forgetting to distribute the negative sign. X cubed plus 5x, and then all over h. Okay, so I'm gonna have to expand this, I guess. Luckily, we did that review a little while back, so hopefully the way to expand this is familiar to you. Limit as h approaches 0. I'm gonna make this bigger. All right, here we go. So it's 1, 3, 3, 1. So it's gonna be x cubed plus 3x squared h plus 3x h squared plus h cubed. So that's 1, 3, 3, 1. And then x cubed down to x to the 0, h to the 0 up to h cubed. H to the 0 sounds like a rap lyric. Okay, and then minus x cubed minus 5x. That's why we put that in parentheses, so we don't mess that up. Okay, if you did that part right, everything that doesn't have an h is going to cross out. So let's see if it does. I did it wrong because I forgot. I forgot the second part there. All right, let me go back here. I'm gonna need a much longer bar here. I got plus 5x plus 5h minus x cubed minus 5x. So when I was looking at it and I was telling you that you messed up if you forgot something, I realized that I had messed up because I had a minus 5x and I didn't see anything that I was going to cancel it with. But now I can see I have an x cubed and a minus x cubed. Those are going to be gone. I have a I have 5x minus 5x. Those are going to be gone. So now I know that I did it right, or at least I didn't definitely do it wrong. Limit as h approaches 0. All right, 3x. You know what? Can I simplify the h's out? I think I'm going to do that. I'm going to save myself a step. So let's do parentheses because there's no fraction anymore. So there's no like implied grouping symbols. So now I usually put it in parentheses if I remember to. 3x squared plus 3xh plus h squared plus 5. Okay. Now, if h approaches 0, everything with an h in it will just go away because it'll be 0. So we get 3x squared plus 5. Whew, okay. So we made a mistake along the way, but that's fine because we noticed it. I definitely didn't intentionally do that. That was just like absent-minded, but it happens. So this is f prime of x is 3x squared plus 5. All right, that's half of our answer, right? Or a third of our answer, some amount of our answer. Okay, so we did this, check. Show that f of x is differentiable. All right, so what does it mean for a function to be differentiable? It means that at every point in the domain of f of x, f prime of x exists. Okay, so what I'm gonna need to know is I'm gonna need to know the domain of f of x. So f of x is a polynomial, which means its domain is all reals. So let's start with that. Since domain of f of x is all reals, so x is an element of the reals, and domain of f prime of x is an element of the reals. Okay, so how do I know that the domain of f prime is all reals? Well, f prime is also a polynomial. Fun fact, polynomials have polynomials that are derivatives. They're derivatives until eventually you'll get to 0, and then it's like, is 0 a polynomial? I don't want it to be. So since the domain of this and the domain of that is all reals, f of x is differentiable. So we can just outright say it's a different, I guess I should write it, differentiable. Right? So if the domain of f prime, right, the domain of f was all reals. If the domain of f prime was all reals except for 2, like for some reason the derivative doesn't exist at 2, then the function wouldn't be differentiable on its domain and therefore is not differentiable. It takes one, it's like one bad apple ruins the bunch. All right, and then finally, tangent line at x equals -1. All right, so let's do this. F of -1. F of -1 is -1 minus 5 is -6. F prime of -1 is, so I'm using F prime, which is get over there. So F prime of -1 is 3 plus 5 is 8. So our tangent line is going to be y minus -6. So y plus 6 is 8x minus -1 or plus 1. There you go. That's our tangent line. So these are all very common questions to answer. I'm going to come back in the next video and do the next part of the notes because I feel like this is kind of running a little bit long. And I will see you then. All right. Till we meet again.